Hello all, thanks Sam and Anna for the introduction. Today, together with my colleague Boyang, we will be presenting one of our recent work, which is about the semantic search and how we monitor it in production. Bo, if you go to next slide. Yeah, we have been already introduced. I just want to say that this presentation is based upon our recent paper published in Calling 2020. And I'm going to thank Nikki von Ommeren, one of our collaborators in this work. So in this presentation, we will be covering following topics, actually. I'm going to explain how we started this journey and how we came up with the search engine, what is how our text mining pipeline working, how we expand a search query, how we take care of ranking of our retrieved documents, and at the end, how we monitor our language models in production. So as you know, ING as one of the financial institute is often being asked by authorities how many issues we have registered related to certain topics. You can think of money laundering, data leakage, and so on. And it's going to be a tough and tedious task for our risk officer to create and make a very complete report because of the following challenges. In our financial data, we use a lot of jargons and abbreviations, and issues will be in different languages. And sometimes issues are contextually related to a search term, but they don't have that search term exactly. For instance, if you think of data leakage, there are a lot of issues related to data leakage, but they don't have data leakage as such. And one more thing, after gathering all those documents, they have to spend quite a time to fix false negative and false positive. Therefore, we stepped in to solve this problem, and that's how we came up with a search engine, which automatically suggests relevant keywords to our risk officer, where they can search among them, select among them, and search through all those documents. This search engine contains of three main components. First component is text mining pipeline. The second one is that our word embedding, which we generate similar words from that. And the last one is that how we rank our retrieved documents in terms of relevancy. I will be focusing mainly on part one and partially part two, and Boyang will be covering the rest of the presentation. So how our text mining pipeline works. So as you see, it contains of several stages. At first stage, we detect the languages, and our current search engine support the three languages. It can be easily scaled up to different languages, either by creating a separate pipeline or translating them to English by using some offline translators. The second is that tokenization. What does it mean? It means that we're gonna break long sentences or any sentences into a smaller unit. And you can think of this as smaller unit as a word. Basically, one sentence, we break it down into words. And after that, we label them. And first, label them like labeling based on name entities. You can think of one token can be organization, can be location, a person name. Then we're gonna lematize them. So plural nouns will be converted to singular nouns, and different forms of verbs will be converted to base form. Then we're gonna label stop words like this, of, are, or are. These sort of things will be labeled as a stop words. After that, we're gonna do data anonymization, which is essential in our financial data. We have to anonymize our data if there is a person's name or credit card number and so on. We're gonna do that using regular expression and name entity recognition. After that, we're gonna do abbreviation detection. We're gonna make our text unified. We don't like to have at the same time a full form and also abbreviated one. We're going to detect them, either keep full form or abbreviated one, because down in our further analysis, it will make some noises. Then afterward, we're going to remove stop words. We have already tagged them and labeled them. We're going to get rid of them because they're not going to add any values in our analysis. After that, we do engram detection. We want, for instance, a word like New York will be counted as a one unit and one token. We don't want to have two tokens like New and York. So that's why we do engram detection. For instance, you can think of financial market. We're gonna count financial market as a one unit, not two separated tokens. Then we have a word embedding. Why do we need word embedding? As I discussed before, we're gonna expand our search query to similar words. So how we are going to do that? We're gonna use a word embedding. Word embedding here is a shallow neural network where as an input, we have our text data, and output is a vector space. In this vector space, all the tokens and words are mapped into this vector space. And words which are semantically related to each other, they are much closer to each other. So if you think of a privacy in this figure on top right on top, we're going to look at the privacy and what are the words around or close to privacy. Then we're going to count those words as similar words. We have trained our model on 160K financial data. But the question is that how good is your word embedding? How good is your similar words? We're going to do two different evaluation. One is that intrinsic evaluation, which is simply here is a human judgment. If you think of one term like privacy, we're going to see what would be similar word to privacy in a pre-trained models like Word2Vec, which is trained on Google News, Glove, which is trained on Wikipedia, and our Word2Vec model, which is trained on our domain-specific data. As you can see that the word generated from our domain-specific is more relevant to our banking domain and a financial domain. By the way, those numerical values in the parentheses shows our similarity score. 0 means that they are dissimilar, and 1 means that they are identical. Another way of evaluating your word embedding, our word embedding, was basically applying this word embedding for downstream tasks, like for a classification perspective. So here we use our embedding layer followed by GRU architecture, and we realize that our custom word embedding only trained on 160K documents perform as good as pre-trained one, which trained on millions and billions of records. Then here I will pass it to my colleague Boyang.
Great, thank you, Mojtaba. So this current aspect right now is about term set expansion, but I just want to also bring us back a bit into thinking about this is in the context of information retrieval systems, right? And if you think about the information, this IR system, there are actually two dimensions that I want to mention. One is about sensitivity. The other is about specificity. So far with the similar word expansions, what we are trying to tackle is really about trying to minimizing false negatives, which is focusing on sensitivity. So we want to expand this user queries to bring in more queries terms to encompass a larger scope so that we can get as much of the relevant documents back as possible. The other dimension is about then specificity, and we try to tackle this using relevance ranking. So imagine you have now all the returning documents, but not 100% of them are perhaps relevant to the query. So we want to rank the returning documents so that the most relevant documents appear on the top of the list. And so this is the last part that I'm going to talk about, which is relevance ranking. If you talk about this particular topic, what we're really addressing then is about semantic textual similarity, or STS. And to put it into layman terms, all that really just means we want to compare the queries against a list of documents, right? And just to give you a bit more of the mechanics behind this, it's really rather simple, right? So you can have a list of documents and the queries. the first step in this process of comparing documents and queries is we want to do an encoding step so that we can turn all the textual information into mathematical representation that machines can understand. And in this particular example, the numbers don't matter except to say that now we can turn a mathematical representation of all the text. The next step is to calculate the similarities among them. So what is the similarity between this query corresponding to this document and amongst the other documents as well? Once we have the similarity scores, then we can rank merely just based on those scores. And the higher the similarity score, the higher the ranking, and perhaps the more relevant those documents are against the query. So I'm going to show you a bit deeper in the next two slides that kind of cover a bit more of these two aspects. The next two slides is going to look a bit busy, but I do have a very clear and concrete message for each of them. And that is just really about, for example, the encoding step. You can really categorize down into broadly two categories, which is related to non-embedding based methods or embedding based methods. And this can ranges from very simple techniques such as the TF-IDF models, which are merely based on the term frequencies within the documents, to more sophisticated approaches that's based on neural networks. Really, the only message I want you to take away from this slide is that there is a whole bunch of different methods to address the problem of semantic textual similarity. And the ones that are shown in bold indicate that we have actually tried out a whole bunch of them in our work. Just to go one step deeper into the neural networks, this is another busy slide, but again, the message really here is to highlight that these neural network-based models also have a very diverse set of underlying architectures and the different methods or tasks that are required to train them. And this ranges, for example, where they will ask the model to mask a certain word and ask the model to predict the masked word, or they can ask the model to ask whether this particular sentence is the right sentence following the previous sentence. One last example, perhaps, is question and answer, whether the list of questions, if a given answer is the most appropriate for a given question. So the diversity of the architectures and the diversity of training tasks also differentiate in part the differences that we see in these neural network models. And this can have potential implications when we look at performance in the next couple slides. So with this in mind, the first thing we want to do is using this diversity of different models to first evaluate the time performance. So as an experiment, we actually timed how long it would take for a variety of different algorithms to encode about 30,000 records. You can see here, for example, the very simple algorithms such as the TF-IDF is essentially almost instantaneous in terms of their encoding time. But what is most striking is that if you look at the BERT models or BERT-based models, you see that the time performance is actually really slow. And in one instance, it can take up to 7 hours to merely encode only 30,000 documents. So just keep this in mind, and these things can become really time prohibitive when you're thinking about trying to build productionized models that have to run at a much greater speed. So this is even independent of how well they will perform in terms of their ranking capabilities. So time performance aside, the next thing that we can then focus on is just exactly that. What is the ranking capabilities of these algorithms? So before I introduce our results, I do need to spend just one slide on introducing what is the metric that we can use to measure the performance. And this is that slide showing here, which is precision at K and also the average precision. So I just want to bring to your attention the bottom half of the slide, which is this graphic here. On the x-axis is basically indicating the number of documents you're returning. The y-axis represents the proportion of documents returned that are the most relevant. So the way that you read this plot, for example, is if you're returning one document, the question is whether that document is relevant or not relevant. If it is, that means 100% of that document is relevant. Otherwise, it's 0. And if you say returning now 2 documents, you can ask the same question. If both documents are relevant, they will have 100% precision. If only one of them are, that will be about 50% and 0. So you can repeat this procedure, so on and so forth. In this particular example, go up to 175 documents. The only thing you have to keep in mind in this particular evaluation is that the higher the curve, the better the ranking. So the red curve here indicates is a very good ranking algorithm compared to something that's in blue here. Now, we can also turn this graphical representation of the assessment into a single number. And I won't go into the mathematics here, except to say that we can also look at the average precision to evaluate whether one algorithm is better than the other. So the higher the average precision, the better the ranking. So now on with the results. So we manually annotated the topics of hundreds of documents and assessed the ranking algorithms across a broad set of different classes. So there are a couple key points I want to highlight. The first is that if you look at the very simple algorithms, such as the TF-IDFs, or even our domain-specific word embeddings, you see that they were actually performing rather poorly. And the reason for that is, even though they were good at picking out certain words and relative to their frequencies, they weren't very good at understanding context. So in this particular example, we're asking the algorithm to picking out, for example, documents related to statistical models. And there are, however, other documents that mention the word model in other contexts. There are models that's related to the business model, related to the model number of a device, such as a mobile phone or ATM, that has no really the same context as a mathematical or statistical model that we're trying to find. And these models fail really bad in those very context-dependent queries. And then you can also see that for BERT models, they do actually improve the performance, but keep in mind, they are actually very time intensive and they're rather takes a very long time. Then if you look at these universal sentence encoders and different variants of them, these are created by Google, you can see that actually outcompete the BERT models. In addition, there's also different variations among them. So a couple slides earlier, I told you about there are many different underlying architectures and different training tasks and different input data that's used to build these models. And these different versions reflect those differences. So the different performances that you're observing here is in part indicative of those variations that's underlying that. So all in all, from this particular set of evaluations with many different kind of queries, we eventually decided on using the multilingual universal sentence encoder, which has a fairly good performance and is also capable of processing multiple different languages. So the next question that we asked is, can we do even better? So I won't have time to go into the details of this slide, except to say that we did try to actually use an additional Siamese architecture to fine-tune on the MUSE models on the GPUs with a particular next sentence prediction tasks. If you don't understand what I said just now, it doesn't really, it's not the most important thing, except to say that we did try to fine-tune our models, but the performance was actually still comparable to that of the pre-trained models. So we did not dive deeper into fine-tuning further in that case. So putting all these together, we have shown you so far that we have built an entire end-to-end semantic search system where we have an underlying text mining pipeline to pre-process everything. We have a word embedding system for term-set expansion, and also a sentence-based model for ranking. There are two additional points I want to point out. One is that in terms of the implementation for the ranking, we actually also use the package FICE that was created by Facebook, which really enables a high volume real-time similarity calculations and the indexing in memory of the documents. And this is basically can be then used app production in real time. The other comment is that in order to stay relevant with our word embeddings to suggest the most relevant similar terms, we actually continuously train our word embedding models with new, fresh data. However, because of this approach, this also brings in another issue, is that if we're going to keep on training our models, we have to make sure that the newly trained word embeddings do not degrade the performance. So in this case, it's challenging because we're not simply building a machine learning model where we can just measure its accuracy or the AUCs. Here, we're building models where we have to understand the interrelationships among the words and make sure those interrelationships don't change. So we have to develop additional novel techniques in order to measure the stability of our word embeddings. And that's what I'm going to talk about in the next couple of slides. So in order to measure the stability of word embeddings, we first need to understand what is the baseline variability from run to run on the same data. And that's exactly what you're seeing here on the left, is we built two independent word-to-vec models from different runs, but on the same data. Each data point here represents a pair of words with their cosine similarity values based on either the first run of building the model or the second run, right? And this spread, effectively, then what you're seeing is the intrinsic variability that you can observe with the data. Now, in order to have a positive control, we ask the question, can we bring in another model that's very drastically different? And does that change the behavior that we're seeing in this visualization? And that's indeed what we did. So now we're comparing the same custom trained model, but now compared against a word-to-vec model that was trained on Google News. So a completely different input data set, right? And you can see this very vast difference in terms of their relationships. So knowing this, we wondered then if we can have a way to quantify these differences, effectively what we can do then is monitoring the intra-relationships among the word embeddings themselves between old and new models. So what we can do effectively is we can bootstrap this baseline to generate node distributions and measure how much deviation from distributions that's generated based on new models. So I'm going to animate what I just said in the next couple slides. And that effectively is the following, right? This is the same plot that we showed you earlier, where we sampled m different words and compared between different runs, which give us a baseline. But instead of just doing it once, we can actually bootstrap to sample many different times. And also then we can do a quadrant to look at different slices of the similarity quadrants. And for each quadrant, we can generate a distribution of the correlations among them. The details of this, I won't have too much time to go into detail, except to say that essentially what we have done here is to convert via Bootstrap method to generate a underlying node distribution that we can use to compare against. Right. So what that would entail then is by comparing the distribution from models that was done run to run on the same data, we can generate the underlying node distribution. And if we now also repeat the same procedure, but looking at what is the distribution between an old versus new model, then we can generate a distribution for the test distribution. And then we can ask the question, can we then measure that distances, right? And this is essentially the plot, I think that's the most clear in the end, that you can also see the differences. So the underlying gray is the node distribution that we can observe that provides the baseline variabilities that we observe. And you can compare this in contrast with different set of models. So if we're comparing a new versus new model training on slightly different input data sets, you can see that the distributional shifts are rather small. However, if you're comparing this against a model that's based on, say, the Google News input data, you can see a very vastly different distribution. And we can quantify this using the Jensen-Shannon divergence. And you can also quantitatively see these differences. So by defining a threshold, then we can use this as a way to monitor any particular intrinsic drifts that we observe in our word embeddings. And this is now being used on production for our monitoring procedures. So to conclude, what we have shown you guys in this 30 minutes is the following, is that we have presented an end-to-end semantic information retrieval system that's currently used for risk management. There are three aspects that we highlighted. One is using term set similarity to address the issue of sensitivity or false negatives by using domain-specific word embeddings. We used relevance ranking algorithms to address specificity, and this is related to false positives. And this is done via a pre-trained multilingual universal sentence encoders. Because we're continuously training the word embedding models, we've also presented to you guys a novel statistical approach we're using to monitor continuously the trained models that's currently on production. And this is done via a bootstrap sampling approach of the node distributions and with the distances of the distributions measured based on a Jensen-Shannon divergence. All the work that we have shown you guys today have also been published recently. So we actually also attended the cooling conference last week. And this particular work is also published in the proceedings as well. So with that, I would just like to highlight all the folks that was involved in this work. So this is the core team, but we also have additional engineers who have also helped us along with this journey. Mojtaba is from People Analytics. Me and Nikki are from One-to-One Analytics. And this also was a really wonderful collaboration that came together to build this entire system with lots of moving parts together. So with that, then we would be open for now questions. Thank you so much for listening.
Thank you, Boyang and Mojtaba, for the amazing presentation on semantic search with domain-specific embedded models and production monitoring in FinTech. I'm sorry for the beginning. There was quite of noise, a lot of noise. I've got new headsets, so hopefully we can make it. And we have a lot of questions. So if you are ready, somebody was already asking about the link of your presentation. If you could share it. Boyang, maybe, to your publication.
Yes, so I think this will be, so if you have the QR code here, you can scan it. And I think if you pause the YouTube later on and go back to this,
Great.
you can take this and this links to the publication. It has all the information.
Excellent. So we go immediately to the first question. It's how token assignment is done. For example, a name Alex should be under the entity person.
Mojtaba, perhaps that's about token.
Yes, indeed. That's how it has been done, actually. In principle, name Alex has to be recognized as a name person.
Okay, and then somebody else is asking, I think, maybe the same questions about entity recognition to extract interesting data.
Interesting data, to be honest, I'm not sure what does it mean, interesting data, but I mean, you can do to kind of make some insight from your text data, because you can extract some location, organization, name of person, date, and also money. You can use it for some getting some insight from your text data, but interesting data, I'm not entirely sure what does it mean.
You can also check it on the chat and maybe respond better to him afterwards. Last questions, because we've got 2 minutes left. We have, how do you ensure the queries of answers share the same embedding space?
The queries and the questions, so we use the same embedding. So if the question is about whether they're aligned or not, I think that's in part if we are using the sentence embeddings to encode both the queries as well as the documents. So if we're looking at these similarities, if they're similar, they're by that definition close together in the same embedding space, if that's the question.
And the last questions we have is how the word Alex is labeled with person entity.
Well, I think it's a pre-trained model behind this algorithm. So, I mean, there is a model trained that, okay, if there is a token coming maybe at the capital format, starting with capital, or being at some specific part of a sentence, it can be potentially a name, actually. So this model trained on number of data, amount of data, then there you can use it for any data as well.
Great. I see the door. Kedem has added the link to this paper. So thank you so much for doing that. And thank you guys for this amazing presentation. Also want to thank Nikki that she was in your team, and she was also one of our star speakers in one of the old presentation of the online data meetup. Okay,